Hello everyone, my name is Mansiba Gohil and today I will be talking about my simulation project which involves the analysis of half-wave rectifier, full-wave bridge rectifier and full-wave center-tapped rectifier, ripple voltage, DC voltage, PIV and rectification efficiency will be taken as the parameters of comparison. Firstly, what is rectifier? Rectifier is an electrical device composed of one or more diodes that converts the AC alternating current to direct current, DC current. Now there are two major types of rectifiers. First one is the half wave rectifier and the second is full wave rectifiers. Full wave rectifier can be divided into more two types, which are the full wave bridge rectifier and full wave center tap rectifier. Now I will simulate the circuit of half wave rectifier in the NI multisim. Before doing that, I'd explain what is half wave rectifier. Half wave rectifier is defined as a type of rectifier that allows one half cycle of an AC voltage waveform to pass while blocking the other half cycle. uh, what that means, it means that it removes one half of the input signal to establish a DC signal. Now, in multisim, I have taken an AC voltage which is providing the voltage in RMS value. I have taken a step down transformer and I have connected it to a diode which is in I have also taken a resistor which is in series, and in order to get the sign for in order to get the waveforms, I have taken an oscilloscope and I have connected it with the I have connected its first channel with transformers secondary part, and the second channel with the blue wire is connected across the resistance in order to get the output voltage. I have also taken a multimeter to measure the voltage across the resistance. I have grounded the circuit. Now simulating the circuit, we can see that we are getting the red waveforms which are in the sinusoidal forms, and also we are getting the blue waveforms. If I just change, uh, now you can see that the blue waveforms are not showing the negative part of the cycle, meaning that half wave rectifier has cut down the negative part of the cycle. Now if I measure the voltage across a waveform, then the input we have is 14.193 volt, which you can see, which will be in the secondary part of the cycle, which is in the RMS value, as we are providing the circuit the RMS value, and also the output will also be in the RMS value. Now, coming to the analysis, I will talk about the circuit. Now, how can we find the RMS value of the input and of the output? In order to do that, as we have taken the step down transformer, we can simply use the formula NS by NP equals to VS by VP, and we can find the VS value, which will be in the RMS. And in order to find the peak value, we simply need to multiply the RMS value by root 2. Now, if we want to find the voltage across the diode, in order to do that, the calculation will be simple. We just need to do the subtraction. Vs peak minus Vb will give us the value of voltage across the resistance. Now, if we talk about the efficiency of the half-wave rectifier, firstly, what is efficiency? Efficiency is nothing uh, the, the ratio of power output by power input. By what do we mean in half-wave rectifier? Uh, in the half-wave rectifier, the DC power available at the load to the input AC power. That would be the ratio we need in order to get the efficiency of half-wave rectifier. Now, as we know, power equals to I square R. I have done the calculation as shown, and we will get the efficiency uh, formula by 4 by pi square into 100, which is in percentage, and the final answer is 40.56 percentage. Now, as you can see, that is a quite low value for the half-wave. That is a quite low value which we get in the half-wave rectifier for the efficiency part. Now, coming to the PIV, meaning peak inverse voltage, also known as the peak reverse voltage, PRV. Now, what do we mean by PIV? PIV is the maximum reverse bias voltage that can be applied across the diode before entering the Zener or breakdown region. Now, in order to explain that, I have taken a simple half-wave rectifier circuit, and as we want to find the PIV, the diode will be in the negative cycle, meaning that it will be in the reverse bias, so the diode will act as an open circuit. And I have taken V as the voltage across the diode. As I have shown, V equals to as I have shown, PIV will be equal to P and will be equal to V, and in the second circuit V will be equal to Vm. So we find that PIV is equal to Vm. But there is one condition which says that in order to protect the diode, the PI value should be equal or greater than Vm, and we do this to avoid the diode from being damaged or burned out. Now I will talk about the ripple factor of the half-wave rectifier. Now, what is a ripple factor? As we know, the output will have the AC and the DC both components. The ripple factor measures the percentage of AC voltage in the rectified output. So gamma, which is the symbol of the ripple factor, should ideally be 0, and we can find the gamma doing the ratio by taking the ratio of RMS value of AC components present in the output and dividing it by average value of output. Now, as I have shown, I will be equal to IAC plus IDC, and IAC, as shown, as we can see in the circuit, will be equal to IAC will be equal to I minus IDC. Now, in order to find the RMS value, I have simply done the integration, and by simplifying this, we get the IAC RMS value, I RMS square minus IDC square whole root. Now, putting this value in the first equation for the gamma, we get the value I square RMS by I square DC minus 1 whole counts in the under root. As we know, the form factor is I RMS by IDC. We get we can replace it in the formula. Then we will have gamma equal to f dot f whole square minus 1 all in the under root. For the half wave rectifier, the form factor is equal to 1.57. Now doing the calculation, we get the gamma's value 121%. By this, we can see that 121% of the AC component is present in the output current, which is a very high value. And as we do not want any AC component present in the output, we can say that this is one of the disadvantages of the half wave rectifier. Now, as I have taken the multimeter in DC circuit, if we measure the voltage with the multimeter, will we get the same output as we had received in the oscilloscope? No, we do not get the same output as we had in the oscilloscope. And why is that so? That is because the multimeter will measure the average output of the average voltage of the output, and we can do that. I will explain how to get the average output. Average output is also known as the DC voltage. Average voltage is also known as the DC voltage. Now, I have taken an ideal diode's waveform to obtain the expression for the average output voltage. As we know, the half-wave rectifier and the positive cycle will give us the same output as it has in the input, but in the negative cycle, it will cut its half cycle and we will receive 0. So, when the omega t is in the 0 to pi, we will receive Vm. We will see that V0 equals to Vm into sine omega t, and when omega t is between pi to 2 pi, V0 will simply be 0. Now, in order to find the V average, I have done the integration 0 to 2 pi V0 into d omega t by 2 pi minus 0. Now, simplifying that term, we get V average equals to Vm by pi. And as we have found, how can we get the V average? How can we receive the Vm? We just need to multiply the RMS value which we receive in the oscilloscope by root 2, and by multiplying that in by root 2, we will receive the Vm, and Vm dividing Vm by pi will give us the average voltage of the half wave rectifier. Now coming to the full wave bridge rectifier, as I said earlier, there are two types. The first one is the full wave bridge rectifier, and the second one is the full wave center tap rectifier. Firstly, I will explain the circuits in the NA multisim, and then we will compare the parameters for it. Here we have the full wave bridge rectifier. In this we can see that there are, as earlier I have taken one AC supply which is providing the voltage in the RMS value. I have taken one step-down transformer. There are 4 diodes, and as before I have taken an oscilloscope, and its first channel is connected to the input and the second channel is connected across the resistor in order to get the output. Now both are grounded, and as we can see there are 4 diodes. Two of them are in the forward bias, and the 2 of them are in the reverse bias. D1 and D2 here will be in the forward bias, and D3 and D4 will be in the reverse bias. Now when we have the positive half cycle, the D1 and D2 will will be in the on position, whereas D4 and D3 will be off and will work as an open circuit. When we have the negative half cycle, the opposite of that happens. D1 and D2 will work as an open circuit, and D3 and D4 will work in the on condition. So In the half wave rectifier, we were only getting the positive half cycles output, and the negative half cycle was cut out. But in the full wave rectifier, we will receive both cycles output, and both will be in the both will be in the positive cycle, which we can see by running the circuit. As we can see, here we are seeing that the blue line is constantly on the upper side of the graph. We are not seeing any minus, or in the negative cycle we are not seeing any uh, negative form. So we are simply receiving the positive cycle, which means that the full wave rectifier is going to give us the output in the positive and the negative half cycle too. Now we will discuss about the full wave center tapped rectifier. As earlier, I have taken the AC supply voltage. I have taken step down voltage, which is 1 and 2s, and I have taken two diodes. And as earlier, I have taken an oscilloscope. Its first channel is connected across the secondary part of the transistor in order to get the input, and the second channel is connected across the resistor in order to get the output, which is indicated by uh, the wire of it is indicated by the blue color. Now in this also, as we have taken two diodes, in the first positive half cycle, D1 will be on and D2 will work as an off condition, which will work as open circuit, and in the negative half cycle, D1 will be off and D2 will be on. So same thing will happen in the center tapped rectifier too. We will receive output in positive and negative cycle. Also, if we run the circuit, we will be able to check if we get the desired output or not. As we can see here, that there is no negative part of the sinusoidal waveform. We are only receiving the first half part of the waveform, meaning that we are only receiving the pulsating DC by the center tap and bridge full wave rectifiers. Now, if we come to the part of the efficiency, as I have explained earlier what efficiency is, I will just do the calculations for it by using the formula I had said earlier. And by doing the calculation, we get n 8 by pi square into 100%, meaning that efficiency is 81.13%, which is quite high. As we saw earlier, for the half wave rectifier, the efficiency was only 40.56%. So there is a huge increase in the efficiency. Now, if we talk about the PIV of the full wave rectifier, as I explained earlier, peak inverse voltage, is known as the PIV. Now, this is the calculation for the center tapped rectifier. For this first half, I have taken the D1 will work as an open circuit when we give the output in the negative half cycle, and D2 will work as in the ideal form will work as a short circuit. And by doing that calculation, we will receive that PIV is equals to 2 Vm, meaning as we had taken one condition earlier, PIV should be equal to 2 Vm or greater than 2 Vm. We can see this change in the half wave rectifier. The PIV should be equal to Vm or greater than Vm. Now we will see the PIV for the full wave rectifier. As I have drawn the circuit here, we can see that the PIV for the full wave rectifier will also be same as we had got in the half wave rectifier. The PIV should be greater or equal to Vm. Vm meaning that the maximum voltage provided to the circuit before the circuit enters the zener region, which will be the PIV of the circuit. Now coming to the ripple factor of the full wave rectifier. Uh, for the ripple factor, the bridge full wave bridge rectifier and full wave center step rectifier will have the same value. So doing this same calculation for both, we get the gamma equals to 41.1 percentage. And as we saw earlier, for the half wave rectifier, we had received the gamma as 121%. Now we can here see that in the full wave rectifier, the gamma is reduced by 73 percentage. So the AC component in the output is quite less than the half wave rectifier. Now coming to the average output of the full wave rectifier, as I had explained in the circuit, that the output we receive is the is the first half cycle, and we do not receive any negative or zero. So for that, when the omega t is in the 0 to pi, is between the 0 to pi, v0 is equals to vm into sine omega t, and when pi to omega t is when pi to 2 pi, uh, when omega t is between pi to 2 pi, we will receive the same value for the v0. Now calculating the v average, as I have said earlier, that it is also known as the DC voltage we receive. V average equals to 2 Vm by pi. And for the half wave rectifier, we had seen that the V average was Vm by pi. So these are the major differences which are in the half wave rectifier and the full wave rectifier. Thank you.